Hello students. So today we'll discuss the SN2 mechanism for the nucleophilic substitution reaction. As we know that the nucleophilic substitution reaction, that is SN reaction, occurs by the two mechanisms, or we can say that the two mechanisms are proposed for the nucleophilic substitution reaction. So one method is, or one mechanism is, it is SN1 mechanism or SN1 reaction. See, this is also known as a unimolecular nucleophilic substitution mechanism or substitution reaction. And the another method is, or another mechanism is SN2 mechanism. This is also known as a bimolecular nucleophilic substitution reaction or mechanism. See, firstly, before discussing the mechanism, here we'll discuss some important features of SN2 mechanism. See, the important features for the SN2 mechanism is, firstly, in this SN2 mechanism, the old bond breaking and new bond formation both occurs simultaneously. And always remember here, in SN2 mechanism, the nucleophile, see here we are discussing the nucleophilic substitution reaction. In this case, the leaving group is replaced by the nucleophile. So here the nucleophile, this attacks the substrate. This attacks the substrate molecule from trans side to leaving group. Leaving group is the group which is to be replaced. Atom or group which is to be replaced, that one is known as leaving group. So, and here, as we know, in this method, the old bond breaking and new bond formation both are occurring simultaneously. So, there will be a situation or condition when old bond is not completely broken and new bond is not completely formed. So that type of situation or that type of condition is known as transition state. So the SN2 mechanism is accompanied with formation of one intermediate, or we may call that a transition state, is formed in the SN2 mechanism. This transition state is highly unstable. And finally, and the most important point of the SN2 mechanism, it is that, see, as the here the nucleophile is attacking from the back side, of the leaving group. So what will happen? The group, when the leaving group will be replaced, so the group which is lying on the back side will shift on the front side. Means here this SN2 mechanism is accompanied with, there will be a inversion in configuration. This will accompanied with inversion in configuration. And this inversion means the configuration will get inverted. The group which is lying on the back side will shift on the front side when the leaving group will leave. So this inversion in configuration, it is called Walden inversion. On the other hand, there's another mechanism is SN1 mechanism. In this SN1 mechanism, the racemization occurs, while here inversion in configuration occurs. See, let your nucleophilic substitution reaction is, it is CH3Br, and here this Br is our leaving group. This group is to replaced by the nucleophile, and our nucleophile is OH minus. So this Br will be replaced by the OH, and we will get here the substituted product, and the leaving group Br minus will set free. Okay. So we'll discuss the mechanism by taking this example. I'm taking here a methyl halide or methyl bromide as a substrate molecule, and I'm taking this one as a substrate molecule because the among alkyl halides, this one methyl halide is more reactive, and that's why I'm taking here a methyl halide as a substrate molecule. Why it is more reactive, we'll discuss in another video. Now, remember one thing more here, that the halide ions are, they are very good leaving groups. Okay, and the leaving ability of halide ions, this follows trend. Here the I minus ion is best leaving group among halogens, halide ions. Then Br minus, then Cl minus, and then F minus. I minus is a best leaving group among halides, while this fluoride ion is a very poor leaving group among the halide ions. Now we'll discuss the mechanism, how the SN2 mechanism occurs. See, what happens here. This is CH3 and Br, our substrate molecule. In this substrate molecule, this Br group is our leaving group, means this group is to be replaced. Here the OH minus is a nucleophile, means this OH minus will replace the Br as a Br minus. Now here in this mechanism, SN2 mechanism, the nucleophile approaches from the back side to the leaving group. See here, nucleophile this attacks from the trans side, means from the back side, opposite side to leaving group. So from back side it will attack. And in this method or in this mechanism, the bond breaking and new bond formation occurs simultaneously. See here it is C, H, 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 and here it was Br. The OH minus will attack from the back side, from the trans side, means from opposite side to the leaving group. See here. Now what happens? CBr bond breaking occurs, and at the same time a new bond formation between the OH and carbon occurs. So a condition creates when old bond is not completely broken and this new bond is not completely formed. So this condition, this intermediate, is known as transition state. This transition state is highly unstable. See here, the carbon becomes pentavalent. Now, the formation of the transition state, this step is a slower step. And because it is slow, and as we know, the rate of a reaction is determined in the slower step. So as it is slow, therefore this step of formation of the transition state is rate determining step. And see, now this transition state, as it is unstable, so this one will immediately sets free this Br as Br minus. See, as soon as the leaving group sets free, so the group which is lying on the back side will shift on the front side because the nucleophile is attacking from the back side. So the group which is lying on back side will shift on the front side, and here the configuration will get inverted. So the group which is lying on back side will shift on the front side, and here we can say that inversion in configuration takes place, and this inversion in configuration, this one is called a Walden inversion. Is it clear? And in this way we get here the end substituted product. Here this one was our substrate molecule. Is it clear? In this reaction, as we know, the formation of the transition state is a rate determining step. So therefore, for the reaction, the rate expression for the reaction, this can be written as the rate will be proportional to the product of molar concentration of the reactants in the rate determining step. And in rate determining step, the reactants are CH3Br and OH minus. So the rate will be proportional to the product of molar concentration of the reactants and raised over some power, and that will be equal to the stoichiometric coefficients. Here the stoichiometric coefficients are 1, 1. So here the rate will be proportional to the 1 power of CH3Br and 1 power of the OH minus. Means we can write that the rate will be equal to K CH3Br to the power 1 and OH minus to the power 1. And as we know, the sum of powers in rate equation is called molecularity. So here the powers are 1 and 1. So the molecularity is 2. It means for this reaction the molecularity is 2, and therefore the reaction is called bimolecular nucleophilic substitution reaction or mechanism. So see here in SN2, so 2 means the reaction is having a molecularity 2. Is it clear? And that's why the reaction is known as the bimolecular nucleophilic substitution reaction. Is it clear? Now, relative reactivity of the alkyl halides towards the SN2 mechanism will be discussed in the separate video. Is it clear?